Good morning. Now, so I'm just going to start with the topic numerical differentiation and integration. So we are going to see these topics based by using polynomial interpolation. Let f is a real valued function, okay, and f of xi are given, or means like what is xi? So given where xi's are belonging to closed interval AB, and they may be uniformly spaced, or they may not be uniformly spaced. And so if they are uniformly spaced, you have you can write this a plus ih, with h is equals to b minus a by n. Then we can recall any interpolating polynomial. So since interpolating polynomial are unique, but they may have different type of representations. So you have the following Lagrange form of interpolating polynomial. So Lagrange form of interpolating polynomial, what it will be is Pn is going to be a polynomial of degree less than or equals to n, which is given by summation I equals to 0 to n f of xi times li of x. What are these li of x? Li of x are the cardinal functions, and if you recall li of x definition, that is a product of x minus xj divided by xi minus xj, where this j is running from 0 to n, j is not equals to I. Now the question is, can we use this approximation? So if this approximation for getting the value of function derivative at some nodal point or somewhere in between the interval a to b, or can we have integration? Okay, can we get the integral value of ab? So now the question is, can we approximate f dash of c or integration a to b f of x dx by using interpolating polynomial? The answer is obvious. I mean, like by looking at there, so this is a you can say polynomial representation of given function f, right? So if f is a given, if you know at prior that f is a polynomial of degree n, so we can recover the means like we can get the exact approximation, because we have known that when you have been having a polynomial of degree n, and if you are going to derive the interpolating polynomial of degree less than or equals to n, then you will actually recover the polynomial. It will be giving you the function f itself. So that we have seen somewhere in examples. Let me have an example here. What do you mean by it? Is f of x, let's say it's a polynomial, let's say polynomial of degree 2, x square plus 1, and let's say a is equals to 0 and b is equals to 1. Okay, and let's take the you can say the values at you require midpoint for getting the polynomial of degree 2. So what is a plus b by 2 is 0.5. Okay, so what will be here? So you have, this is x f, So x value is 0, 0.5, 1, and f value is 1. This is 0.5 square plus 1 is 0.25, so 1.25, and 1 square plus 1 is 2. So then if you get this is our equidistant, so we can use also power difference, or you can get the divided differences. So this will be a 0.25 divided by 0.5, right? The length of this. Now this will be 2 minus 1.25, that is 0.75 divided by 0.5. So what it will be, this is 0.5 square, so this is 0.5, and this is some 0.15, right? Now this is the first divided difference table. So now the next is 0.15 minus 0.5, that is going to be is minus 0.35. So if you you can use the value here. These values are first divided difference and third divided difference, and what will be the interpolating polynomial of degree 2, that is going to be equals to is 1 plus 0.5 times x minus 0 plus minus 0.35 times x into x minus 0.5. Okay, now you recall, now this is going to be this is equals to
Sir,
yeah, somewhere
there should be 1.5
here.
at third column, sir. Third column, second entry.
Third column, second entry, 1.5.
Yeah.
Oh, yeah. Okay, yes, yeah, that's great. So 1.5, this is going to be 1. Yeah, thank you. So this is going to be, here value is now 1. And now if you simplify, you will get the x square plus 1 only. Because plus 0.5x and minus 0.5x will get cancelled. So we can recover the actually, if you don't know whether the function is polynomial or not, but if the data means, like, say this we have only taken 3 points. If you go with the 4 points, means like you can go with the like 0, 0.25, 0.5, 0.75, 1. Then you will see the after the second divided difference, at the third divided difference onwards, the all other higher order divided difference will become 0. So we can recover the polynomial. So we can get the approximate value with difference. Okay, but we require some general procedure. Okay, and to approximate the value of function at its derivative. Now, so we know that if you recall that the theorem for polynomial interpolation, and then there, if you recall that error in error, what will be is f of x equals to, if you recall, that is going to be Pn of x plus fn plus 1th derivative at zx, where we are divided by n plus 1 factorial time w of x. What was w? That w is a function of polynomial of degree n plus 1. So I equals to 0 to n, which uses all the points x minus xi. So this denotes the error term. So and then you will, so if this is where gx is lies between x0 to xn. So this is the error term. So using error term, you can exactly write f of x. So where g is gx is lies between the interval x0 to xn, or in particular a to b, if you have x0 equals to a and xn equals to b. But certainly it depends on x as well. And you have used the fact that f is sufficiently time differentiable. So n+1 time differentiability is also used. Okay, so now what it will give us now? So from here, so what if you use the Lagrange form? Okay, so then this will implies f of x equals to, I'm going to use the Lagrange form of interpolating polynomial. That is going to be summation I equals to 0 to n f of xi time li of x plus that this error term, so that we are going to write as en f x as standard we have written earlier as well. Now you can see this right hand side is a polynomial of degree n, so this is a polynomial approximation. Okay, so now you can argue that there are other ways as well for getting the polynomial approximation for a given function. You must have learned in the calculus Taylor series approximation and so on. But that requires the derivative values. Okay, so that will depends on so if you for example, if you go for Taylor series approximation, that will also depend on the derivative value. So you require the higher order derivatives up to how much you want to expand it. Okay, so you require the more dependence there. So here it's only dependence of the values f on xi. Okay, on the nodal points. You don't, so you require the differentiability only to achieve the desired accuracy, how much nodal points are required. So this is what here the idea. Okay, so the polynomial, so always there are some advantages and disadvantages as well. Okay, so we will come later for disadvantages as well. Okay, so here now you can use this as a polynomial approximation, and you can replace f by this, and then you just differentiate, and then you will get it. So polynomial differentiation, this is C infinity differentiable, right? You can differentiate as many times you wish, right? Okay, so now if you're differentiating with respect to x, so see what values x we are looking for is x lies between a to b. We are not looking at outside this interval. Okay, outside this interval, outside xa or on the left of a or left of or right of b. So differentiating with respect to x, what we get is this will imply f dash of x is equals to, the term-wise differentiation is possible, right? Because a finite sum. So you can have this is equals to summation I equals to 0 to n f at xi is a constant, and you have to differentiate li dash of x. Okay, plus that error term differentiation en dash of f at x. So what is en dash at fx is, so it just it can be evaluated. What is en dash f x is going to be, yes, so you are going to differentiate this term, so you have to use the product rule, because this gx is depending on x. Okay, so implicit differentiation. Okay, right, because the total derivative you are taking. So what you have is w dash of x by n plus 1 factorial time f n plus 1th derivative at some c plus w of x by n plus 1 factorial time d by dx of n plus 1th derivative of this g. Now suppose, so let x equals to xi for some I. Then what will happen? So then you can check whether this is en dash f at x equals to xi. The second term get vanished because of w of xi is 0. Okay, so this term will get vanished. So no matter what is the derivative here, but only this term will survive. So this is equals to w dash of xi divided by n plus 1 factorial, and fn plus 1th derivative at z x equals to xi. So zeta is defined, z is depends on xi plus 0. There is no contribution on this, and we can get the explicit expression of this w dash of xi as well. So if you recall, so I just what is so now expression for, so what was the wx is product of I equals to 0 to n x minus xi. So if you differentiate and use the product rule, then what it will be is equals to I equals to 0 to n I not equals to let me have, this is going to be, no, okay, so no, this is not this. It's going to be summation, right? Summation I equals to 0 to n product of j equals to 0 to n j not equals to I x minus xj. So this is going to be the sum of this, right? Now what is w dash at xi? At some of the nodal points. So wherever this at xi, whenever you take any nodal point, so other wherever this x minus xi factor is there, the terms will vanish. So it will remain everywhere except only in the one term, single term. So that is going to be product of j equals to 0 to n, j not equals to I, xi minus xj. So we have the explicit expression for w dash at xi. So with this, what you have is, this will imply the en dash, the error term at xi is equals to this w dash at xi times this, right? So fn plus 1th derivative at z xi divided by n plus 1 factorial time w dash at xi. So w dash at xi can be replaced by this. So we have the explicit expression for everything except this here, because we may or may not be available with the f function itself. So we may not be able to derive the n plus 1 derivative. So only alternate is to approximate. Okay, so what are the approximation available? Forward differences, backward differences, and center difference operator. Okay, so these things you can just carry forward from the previous lectures. Okay, so this is the error term. So if you wish to work with, then you can now, for simplicity, now it was the for journal n, you can take the example for, let's say, n equals to 2, and let's say n equals to 2 means what are the points are x0, x1, x2. Okay, and let's say this I is equals to 1. So we want to estimate the f dash at x1. And further, let's say they are uniformly spaced, means x1 minus x0 is equals to x2 minus x1. Okay, so this is equals to, let's say, some h. Okay, so all these are available with us. So we wish to estimate this f dash of x1. So if you recall here, so what was there is, so you can you have what is L0 of x is x minus x1 into x minus x2 divided by x0 minus x1 into x0 minus x2. So this will imply L0 dash of x is equals to, yes, the product here, right? So this is going to be, the numerator term will be as it is, x0 minus x1 into x0 minus x2, and this will be something like x square, so 2x minus x1 plus x2 x, right? So this will imply what we wish to evaluate is L0 dash at x1. Okay, so L0 dash at x, because we are taking the x value is x1, so that is going to be 2x1 minus x1, that is x1 minus x2. So that is x1 minus x2 divided by x0 minus x1 times x0 minus x2. Now since they are equally spaced, so this is the value is minus h numerator. In the denominator, what is x0 minus x1 is as a minus h, and what is x0 minus x3 is minus 2h. Okay, so this minus will get cancelled, 1h will get cancelled, so what you will get is minus 1 by 2h. That is L0 dash at x1. So similarly for other as well. Okay, so what you will have is, now if I go with the L1 of x is x minus x0 into x minus x2 divided by x1 minus x0 times x1 minus x2. Now this will imply L1 dash of x is equals to 2x minus x0 plus x2. This is, you can use symmetry here. Okay, so x1 minus x0 times x1 minus x0 x2. Now this will imply L1 dash at x1. What is the value? So this is going to be 2x1 minus x0 plus x2, right? So let me go on the next page. So this will imply L1 dash at x1 is equals to, so what is there is 2x1. So one is x1 minus x0 and plus x1 minus x2. So that is going to be, so in the numerator, if you were having is just writing 2x1 minus x0 plus x2. Okay, so numerator is something here, the denominator is something. So if you have x1 minus x0 plus x1 minus x2. Now the first term is h, second term is minus h. So h minus h will come down to be 0. L1 dash. So some numerator is there. So that is going to be x1 minus x0 into x1 minus x2. So this is x1 minus x2, x0 is h, and x1 minus x2 is minus h. So you have in the denominator minus h square. Okay, so now similarly you can go with the L2 at x, that is x minus x0 into x minus x1 divided by x2 minus x0, x2 minus x1, and you can again, so L2 dash at x is again by the similar way 2x minus x0 plus x1 divided by x2 minus x0 was 2h, x2 minus x1 is h. Okay, and now this will imply L2 dash at x1 is going to be, so 2x1 minus x0 minus x1, so x1 minus x0 divided by 2h square, so x1 minus x0 is h, so you will have 1 by 2h. So the f dash at x1 is going to be approximated by f of x0, L0 dash at x1 plus f at x1, right? L1 dash at x1 plus f at x2 times L2 dash at x1. It's approximation. So f of x0, f of x1, and f of x2. These are the values. X0 is x, right? And x2 is x0 plus 2h. Okay. but L naught dash of x1 is 1 by 2 minus 1 by 2h, right? Yeah, minus 1 by 2h, and L2 dash at x1 is 1 by 2h, and this term is 0. So this does not contribute any. So this term is 0 here. So what is there is 1 by 2h time f of x naught plus f of x2. Here minus. Right? So what it will give you if I want to write in terms of x naught only. So this implies f dash at x naught plus h can be approximated by 1 by 2h time f of x naught plus 2h minus f at x naught. Now replace x naught by x naught minus h. So I'm just going to replace, let's say replace x naught equals to, let's say, x minus h. Okay, then what it is kind of shifting only. So that is f dash of x can be approximated by 1 by 2h. So that is f of x plus h minus f at x minus. Now, if you recall, this is nothing but the central difference. Okay, so what was the central difference operator was? Delta f is equals to at x is equals to f of x plus h by 2 minus f at x plus x minus h by 2. Okay, that divide by h was giving you the approximation of better approximation for first order derivative, if you recall. Okay, so if you replace h by 2h, you will get the same form. Okay, and you have also seen this is a better approximation, and you can also verify that error term if you try to fit here is going to be something like a minus f third derivative at zx by 3 factorial h square. So what it tells you, the error term is of third order derivative, means it will exactly approximate the derivatives up to second degree polynomial. This is what actually we have the observation by looking at the error term. Okay, so this error term can be evaluated by, we have the error term, right? So error term, if you go back and check here, so error term is en dash. So e2 dash means e2 dash at f at xi will be f third derivative at zx1, right, at x equal to x, so gx1 divided by 3 factorial time w dash at x1. Okay, so that is going to be x1 minus x naught into x1 minus x2 in this case. Okay, so if I wish to work individually here, so if you go back and check f at x1 going to be at third derivative at zx1 divided by n plus 1, so that is 3 factorial time w dash at x1, that is x1 minus x naught into x2 x1 minus x2. Now see, this is h and this is minus h, so this is going to be minus h square time f third derivative at zx1 divided by 3 factorial. Okay, right. So this tell you that this approximation is good approximation of order h square, and it approximate up to third order, I mean up to second degree polynomial exactly. So for example, let's take the example. So let's have this f of x equals to x square plus 1 again. Okay, and let's find out its derivative by approximating previous. Let's use x equals to means like you wish to find, let's say, f dash at 2. Let's say I want to fish. So if you see the analytically, that is going to be 4. Okay, now let's take in that okay, let's take h equals to 1. Then you have f dash at 2. If you approximate, that is going to be 1 by 2h, f at x plus 1. So x is 2, 2 plus 1 minus f at 2 minus 1. X plus h, x minus h. So h is 1 here, so it is going to be 1 by 2. So f at 3, that is going to be, f at 3 is 9, right? 3 square plus 1, 9 plus 1 is 10, minus f of 1. F of 1 is square plus 1, that is 2. 10 minus 2 is 8, 8 by 2 is 4. You can also work with h equals to 0.5. You can also work with h equals to 0.25. So this will exactly approximate the f dash value. Okay, up to polynomial degree 2. But if you go for higher degree polynomial, it may or may not. Okay, it will not be. Okay, right. So with this example, we have done the numerical differentiation based on the polynomial interpolation technique. Okay, so similarly, you can you can, instead of the Lagrange polynomial, you can also work with the Newton's interpolating polynomial as well. Okay, so I'm not going into that. So I just want to explain that how you can use the Lagrange interpolating polynomial for approximating the derivative of a function. Okay, so it will give you at the nodal points. Okay, so if this is there, you can also go for, so you see, if you wish to go for cubic Hermite interpolation, so you require the good approximation for the derivative values. Okay, so that also you can approximate by here by using this technique. Okay, right. So now let's see the numerical integration. So I hope in during your calculus lectures as well, it has been told that not every function has antiderivative. So you must have learned the fundamental theorem of integral calculus. So what was there is fundamental theorem of integral calculus is f is a, like I say, real valued function, or you can say Riemann integrable. Okay, and then and if you define f of x equals to integration a to x f of t dt, then you have f dash of x is equals to f of x. F will be the antiderivative of this, and at integration a to b f of x dx is equals to, once you know the antiderivative, you can do this. Okay, so it requires, so if you wish to go for this, okay, so continuity is necessary for the given function f. So Riemann integrable, if f is continuous, it is Riemann integrable. Okay, right. Every continuous function is Riemann integrable on a bounded interval, on a closed and bounded interval. Right. So, but there is a there means you can have for what should I mention here is not every elementary function have simple antiderivatives. Okay, so for example, so let's have an example that e to the power x square. Okay, so let's have this elementary function. It's exponential function, and you know what is so it does not have simple antiderivative. If you write here, it's infinite series, that is j equals to 0 to infinity x to the power 2 j divided by j factorial. Right. Now, if you wish to find the antiderivative, f of x is going to be summation j equals to 0 to infinity x to the power 2j plus 1 divided by 2j plus 1 times j factorial. So this is not a simple antiderivative. So, and it is not true that for every infinite series you can perform the term-wise integration, right? What you have done here is term-wise integration you have performed, and you have written this thing, and you are telling that this is going to be the antiderivative of this function e power x square, because you are performing f dash now, so f dash will be f. But this is only true when this series is uniformly convergent, and then there you will occur with this Ristrauss M test and all, okay, that you must have learned in your calculus course. But it is not possible to have antiderivative for every function. So what is our demand? Our demand is we wish to find the integral. So we wish to approximate now integration a to b f of x dx. We wish to approximate this in such a fashion that the approximation depends only on the integrand value, okay, value of the integrands. Okay, so at some points, so what are those points that you can choose as interpolation points and all? Okay, so those things now take place. So the interpolation polynomial will be the good candidate here. Okay, let's see how to approximate this by using the polynomial interpolation. Okay, so we wish to approximate. Okay, so we wish to now approximate f, okay, by an interpolating polynomial that interpolates f at certain set of nodes. Let's f at certain set of nodes. Okay, right. So again, here also the question, see, we are going to choose interpolating polynomial because it will only give you the dependence of the function on means the terms are depending only on the function values. This function is integrand. Okay, but on the other hand, you can also approximate f by using Taylor's approximation and so on. Okay, but that has also a drawback that you require the derivative approximations there, right? So we wish to get a general processor. Okay, again here, right? So now, so let's have the Lagrange form of interpolating polynomial. Okay, so by an interpolating polynomial, say g. Okay, so f is approximated by g, then integration a to b f of x dx will be approximately equals to integration a to b g of x dx. Okay, right. Now what G we are going to choose is, again, we are going to work with the Lagrange form again. Okay, so we G is equals to summation I equals to 0 to n of xi times Li of x. Okay, so again, this x naught, x1, x2, so you have a equals to x naught less than x1 less than x2 less than and so on less than xn equals to b. Okay, right. So with this now, we can, so this implies integration a to b f of x dx. Okay, f of x dx is approximately equals to summation I equals to 0 to n f of xi time, xi is a constant, integration a to b Li of x dx. Now, if you integrate with respect to x, this number is also, this will be also a real number, so that we are going to replace it by capital AI. AI time f of xi, where AI is equals to integrate a to b Li of x dx. I is equals to 0, 1, 2, and so on n. 1, 2, and so on n. Now, if x naught, x1, and so on xn are uniformly spaced, then this formula is named as 3. Then 3 is called Newton Cotes formula. So, which approximate the function by a polynomial of degree less than equals to n, and then integration. Okay, so now for different value of n equals to 1, n equals to 2, n equals to 3, and so on, you will have different type of formulas. Okay, so that we are going to call now. Okay, so means when we are defining this Newton-Cotes formula, means we are now going to work with this, so means they are uniformly spaced. Okay, so now let x naught, x1, and so on xn be a partition of closed interval AB such that a is equals to x naught less than x1 less than and so on less than xn equals to b, and xi is equals to a plus ih, h is equals to b minus a by n. Now the case when n is equals to 1. Okay, the very simple case is n equals to 1, and this is called as trapezoidal rule. That you will soon realize why it is called trapezoidal rule. Okay, that you will soon realize. So n equals to 1 means x naught equals to a and x1 equals to b. And what will be the Lagrange form of the so you have x naught and x1, so L0 of x, what is L0 of x? Is going to be is x minus b divided by b minus a, a minus b, and what is L1 of x is going to be x minus a divided by b minus a. Okay, now what is the formula? What is the interpolating polynomial? Is going to be f at a time x minus b by a minus b plus f of b time x minus a divided by b minus a. Now what we wish to get is, we want to get integration a to b f of x dx. F of x dx. So that is approximated by integration a to b g of x dx, which is equals to f of a time integration to b L0 of x dx plus f of b time integration a to b L1 of x dx. Right? Now, what is there is integration b L0 of x dx. Now you have to calculate, that is we called as a naught. So that is equals to integration a to b x minus b divided by a minus b dx. Now this is going to be, if you this is going to be 1 by a minus b time 2 x minus b whole square, and put upper limit minus lower limit. Okay, so let me write one more step, a to b. So that is going to be b minus a by 2. Similarly, you can show that a1 is equals to integration a to b L1 of x dx is equals to b minus a by 2. So the approximation now, so this will imply integration a to b f of x dx is approximated by, so f of a time b minus a by 2 plus f of b time b minus a by 2. So that is going to be b minus a by 2 time f of a plus f of b. Right? Why it is called trapezoidal rule now? So this is because it is the area of trapezium, right? So you have, this is let's say this is a, and this is here b. So you have, this is here and this is there. What is the area of this trapezium is? This is f of a, this is f of b, this is f of a. So f of a plus f of b by 2 divided time b minus a. Okay, so that is going to be this area of trapezium. So like you have done in Riemann integration, you must have done come across there also in the trapezoidal rule. Okay, so if instead of approximate by rectangles, if you use the trapezium there, so that will give you the trapezoidal rule also there itself as well. Okay, now this is with n equals to 1. Now this is a trapezoidal rule, so you can make the composite trapezoidal rule also. Means you use the partition, you divide now a to b. You have the trapezoidal rule on a single interval now. So let's say a equals to x naught and b equals to xn, and divide this into n equals subinterval. N equal or n may not be equals. Okay, again, they may be uniformly spaced, they may not be uniformly spaced. On each interval, you can measure the area of the trapezium. And then you will, so then if you sum up the area, that will give you the area over the whole interval a to b. Okay, so then summing up this trapezoidal trapezium, area of the trapezium, that will give you the integration a to b f of x dx. Okay, so that is the idea of composite trapezoidal rule. Okay, right. So I'm just going to define now for composite. So now composite trapezoidal rule. Composite trapezoidal rule. We are also going to work with the error term. Okay, so we have on the interval. So we are going to have the interval a to b. Let's say a equals to x naught less than x1 less than x2 and so on less than xn equals to b. Now you can write integration a to b f of x dx is equals to summation I equals to the integration xi minus 1 to xi f of x dx. So I is running from 1 to n. Now on each subinterval you use the trapezoidal rule, that is going to be summation I equals to 1 to n approximated now. So that is going to be xi minus 1 divided by 2 times f of xi plus f of xi minus 1. So this will give you that composite trapezoidal rule. Now if xi minus 1 is equals to h for all I is equals to 1 to n uniformly spaced, then what we have is then integration a to b f of x dx approximately. So this is going to be h now for all n's. H by 2 is out, so h by 2 time. Now if I write the first term, that is going to be f of x1 plus f of x naught. Now the second term is f of x2 plus f of x1, okay, plus f of x3 plus f of x2 and so on, plus f of xn minus 1 plus f of xn. Now see the first term f of x, this f of x naught and f of xn, they are not repeated. Only f of x1 is repeated twice, f of x2 is repeated twice, similarly f of x3 is repeated twice, and f of xn minus 1 also repeated twice. So this is going to be h by 2. F of x naught is f of a plus 2 times summation I equals to 1 to n minus 1 f of xi plus f at b. And now you can replace xi by a plus ih as well. Okay, so if you have the table, how will you use this now? So this is going to be, let's say, the table value is given here. X is given and f is value is given. How will you use this composite trapezoidal rule for integration? So let's say 0, 1, 2, 3, 4. And let's say x square is the function. Okay, so this is 0, 1, 2 square is 4, 3 square is 9, 4 square is 16. Now I want to approximate integration 0 to 4 f of x dx. So analytically what is there is x square x cube by 3, right? X cube by 3 if I take analytical solution 0 to 4. So 0, no contribution, only upper limit. So 4 cube is that is going to be 32. Okay, right. Now if I wish to approximate by the above formula, so what this will imply is this will imply, so I say must say then trapezoidal rule. implies integration 0 to 4 f of x dx is equals to, so h is here is equidistant, so h is equals to 1. So 1 by 2 times f of a, that is f of x naught, that is 0 first value plus last value, right? 0 plus 16. So this is what first value and last values are together, plus 2 times sum of the intermediate values. Okay, so this is 2 times 1 plus 4 plus 9. So what it will be is 22, right? Yeah, so 44 is a sum, and that is 44 by 2 is 22. So there is an error. It is not even approximating the x, right? Second degree polynomial. Why it is so? It must be somewhere in error analysis. Okay? Right. So it is, so what about the identity function, linear function, whether it will approximate? So that you can check one with one more example now. So let's take x value, f value 0, 1, 2, 3. So let's say f of x is equals to 2x. It's a linear polynomial. Okay, so that is 0, 2, 4, 6. Okay, and integration of 0 to 3 f of x dx analytically, what it will be is x square, that is 9, analytical solution. And trapezoidal rule implies integration 0 to 3 f of x dx is approximated by h by 2, so that is again 1 by 2, first value plus last value plus 2 times the intermediate value. So that is going to be 9. So it's approximately exactly the linear polynomial. Okay, so it tells you, and similarly you can go with the constant as well. Okay, so it is giving you the idea that trapezoidal rule will be exact for up to polynomial of d. Okay, right. So let's go for the error term. How will you decide the error now? Where from the error term will come? Because we have used the approximation is interpolation, interpolating polynomials. So error term will be in interpolating polynomial was fn plus 1th derivative at some cx divided by n plus 1 factorial time w of x. That was the error term in interpolating polynomial. Now we have the case for n equals to 1. Okay, n equals to 1. So for the case n equals to 1, error term will be f second derivative at some zx by n equals to 1. So that is 2 factorial. And that wx is what? That is x minus x naught into x minus x. Right. That is a w of x. Okay, right. Now we wish to get the error term for this. So now what you can do is, so this so error term on single interval we are talking, okay, on a single interval on AB for trapezoidal rule. What it will be is integration a to b f double dash at z by 2 factorial x minus a into x minus b. That is going to be the error term. How will we work with it? Okay. So now we are going to use the mean value theorem here for integrals. So you must have come across from the mean value theorem for integral calculus, and which has the application. I'm going to state here that I just want to state one result here. If f, real valued function f, is continuous and g is an integrable function, is Riemann integrable function, that does not change sign on closed interval, means it remains either non-negative or non-positive. Okay, then there exists C in open interval AB such that integration a to b f of x g of x dx is equals to f of c times integration a to b g of x. Okay, and the proof of this result is also very simple. It's a combination of it's going to be use the mean value theorem, because mean value theorem as well as what's it called, is intermediate value theorem, because f is continuous on a closed interval, it attains its bounds. Okay, and then you can work with the results. So, okay, so it's hint I can give you here. So if you used to go, so you say m less than equals to f of x less than equals to capital M, then what will happen is g does not change sign. So m into g of x less than equals to f of x into g of x less than equals to m g of x. So you can assume that g is a positive. So this certainly integration a to b, integration a to b, integration a to b dx. Right? Okay. Now, so this is going to, so this you can call, this is going to be, you can say, what is C? Small m less than equals to capital M. So you can here. So if you have this integral value is 0, then nothing to prove. Okay. So you assume that this integral value is non-zero. Okay. And so if you assume that this integral value is non-zero, so without loss of generality, you can assume that integration a to b f of x g of x dx is non-zero. Okay, right. Okay, now what you call is let. Also, you can have integration a to b g of x dx. Let's say this is non-zero. Okay, so let this is equals to I. If it is non-zero, you can definitely say, okay, let's say this I is a non-zero number. Okay, right. So what it tells you is, so this will imply m times I less than equals to integration a to b f of x g of x dx less than equals to capital M times I. So you can set this I on this side. Since g is a non-negative function, so this is either greater than 0 or less than 0. Okay, so that you can work with it. Now, what you can do, so this will be small m less than equals to 1 by I integration a to b f of x times g of x dx less than equals to capital M. Now, since f is continuous function, so intermediate value theorem tells you and that f certainly assume this value for some point C in AB. There exists, the intermediate value theorem tells you that there exists C belongs to upper interval AB such that this 1 by I integration A to B f of x times g of x dx is equals to f of C. And hence we are done. Okay. So do you have any question here? So now, if not there, so now we are ready to establish the result for error term, and then we will close. Okay, right. So now, if see in a trapezoidal rule, you are assuming that second derivative is continuous. So if second derivative is continuous, you assume that second derivative is continuous. That is going to be there exists some point C such that this second derivative C is out, some or C, or you can say Z by 2, and integration A to B times x minus A into x minus B. See, all the conditions of the mean value theorem, what we have stated is true here, because x minus A into x minus B, so x is like dx here, right? This does not change sign, right? X minus B, x is lies between A to B, so x minus A is greater than 0, x minus B is less than 0, so there is always negative number, does not change sign. So it's an integrable polynomial. Okay, and then you can just integrate this, you will get the error term. Okay, right. Now I see some question, why it was equal to f of C. Which one? The last here? Yeah. Yeah. So if you recall this intermediate value theorem, so intermediate value theorem from the calculus. Okay, f is continuous and let k is such that, okay, and it is a continuous, so uniformly continuous, and it is bounds. So then what will happen is then and let small m less than equals to k less than equals to capital M, where this small m and capital M are such that small m less than equals to f of x less than equals to capital. So for every k, any point in between, there always, so f assumes every value in between. Okay, so this is the application of intermediate value theorem. Okay, yeah, thank you. So with this here, so now you integrate this and verify that this is going to be, so going to write down now, this is going to be by using application. So I'm just going to now so error in trapezoidal rule is integration A to B f second derivative at cx by 2 x minus A into x minus B dx, and this is equals to f second derivative at some z by 2 integration A to B x minus A into x minus B dx, where z lies between open interval AB. Now if you integrate and put upper limit minus lower limit, what you will get is minus f second derivative at z by 12 times b minus a whole cube. Okay, now this is going to be is equals to minus f second derivative at c by 3 b minus a time b minus a square by 4. So that is h square in particular. Okay, right. Now you can talk about the error in composite trapezoidal rule now. Okay, that's a final finally we are going to give the error in now composite trapezoidal rule. So if you talk about the interval xi minus 1 to xi, so on xi minus 1 to xi, so you call this as ei, that is going to be minus f second derivative at zi, you can say depending on this I interval, divided by 12 times b minus a whole cube, means you have xi minus 1 whole cube. Okay, now if you say they are uniformly spaced, and let so we are having a uniformly spaced, okay, xi minus 1 is equals to h for all I is equals to 1 to n. Then what is ei is minus f second derivative at ci by 12 times h cube. So on interval a to b, e is equals to summation I is equals to 1 to n ei, right, because I is running from 1 to n here. So that is going to be minus 1 by 12 h cube summation I equals to 1 to n f second derivative at zi. Now since f second derivative is continuous, and then you can show that there exists a z in between AB such that this f second derivative at zi can be approximated by f second derivative at z. So again you can apply the mean value theorem here, that it will be approximated by, you can say, minus 1 by 12 h cube n time f second derivative at z for some z in AB. Now what is n is? So here n is you have to determine, okay, how many number of intervals you are going to take. Now you can adjust n with the h cube as well. So one is b minus a whole cube by n cube. So what n got cancelled, so you have its total error will be, this implies, writing you, this is going to be minus 1 by 12 b minus a times h square f second derivative at z, where z is some point in interval a to b. Okay, now the final exercise here is that you can determine, okay, you can look at it, okay, and we can work it in the next class. So evaluate 1 by ln3 integration 1 to 3 x inverse dx by composite trapezoidal rule with h equals to 1, h equals to 0.5 and h equals to 0.25. Also analyze the error. Okay, so here we close this lecture now. Okay, yeah, thank you for this.